Good morning, everybody, and welcome to our webinar. And we are happy to have you for our March edition of the Pigment 101 webinar. Today, we're going to take a deeper dive in quinacridone pigment chemistry and products and impact on your formulations. So we are recording this session, so all of those in attendance today will receive a link to the recording as well as the PDF of the presentation. And as always, if you have any questions along the way, feel free to go ahead and put them in the chat box, and I'll take care of them at the end of the presentation. So with respect to quinacridone pigments, we've done this one in several years ago. I just wanted to update and refresh it and bring you some deeper information about the impact on your formulation and how the different products can help in your choices of pigment. Let's see. There we go. So the quinacridone pigments are part of the polycyclic for a family of organic pigments. They are a high performance pigment, and thus they will give you some of those added additional properties that you might be looking for in your formulation. There we go. So as far as being part of the polycyclic class of pigments, these are unique in the fact that the chromophore is embedded in that structural frame. The total class of polycyclic pigments are on the smaller side. They're probably a little bit less than a quarter of the organic pigment volume out there. However, they come with some advantages. They have a very high value in use due to their performance properties as well as the higher strength that comes along with them. So additional value in use comes with these pigments. From a color space perspective, I've highlighted a few of the quinacridones in the red color space. So they do span from the yellow shade to the blue shade in the red color space, as well as in the red shade in the violet color space with the beta crystal of the violet 19. As I mentioned, these are high performance pigments, and in this particular example, these are on the high side of the high performance pigments. So they do bring with them high light fastness, high weather fastness, high heat resistance, and high fastness to solvents and chemicals. So when you're selecting a pigment, of course, it's only going to be valuable to your end customer if it performs in the manner which you try to your intent for that application is in there. So if it doesn't give you what you're looking for, it's not valuable to the customer. And each marketplace, of course, does have their own unique requirements. And so it's the formulator's job to make sure that the formula is correct and meets all the technical requirements. And it's pigment supplier's job to provide the support needed to help you choose that appropriate pigment. So the other thing to consider is that in every pigment color index, you're going to find a lot of products in that class of pigment chemistry. And you're going to find at least one grade that has the properties that you are looking for in there. So you're going to get the performance based on the chemistry, as well as the choices of finishing that are done for that particular pigment product, I should say. So as far as an introduction into quinacridones, they were first synthesized in 1935. DuPont brought that forward with new synthesis options, new polymorphism, and established that photochemical stability. In 1958, it was the introduction of two crystal modifications that are being used, well used today for commercial on a commercial basis. There are three major chemical constitutions with respect to quinacridones. The unsubstituted uh, quinacridones, the 2,9 position dichloro substituted quinacridones, and the 2,9 dimethyl substituted quinacridones. In addition, there are modifications in solid solutions in quinacridone chemistries, and all of these areas will be reviewed in the presentation today. So some quick notable properties with respect to these, and I mentioned them all, some of them already. These do have extremely outstanding chemical and photostability. Low solubility, and they obviously offer very attractive color options for your formulations. As far as the quinacridone family itself, a couple things to consider. We have a basic backbone structure with options to make substitutions on four of the positionings. And it's this choice of the type of position, the type and position of these substitutions dictate what that particular quinacridone will look like in terms of hue as well as performance properties. So if we start with the unsubstituted, that's going to be our pigment violet 19, and they span from the red shade to the violet shade, and that's due to the polymorphism of that particular crystal. The gamma crystal is the red shade, or the red shade yellow, if some people call it. The beta crystal is to the violet side, so a blue shade of hue, all due to that polymorphism. If we start with the R2 and the R9 positioning, so top right, bottom left of the structure, and we put on that a methyl groups, that's where we're going to get the pigment red 122, which gives us a very lovely magenta high strength color positioning. If we stay with that R2, R9, the top right, bottom left, but substitute in chlorine, there we receive the pigment red 202. That provides us with a very brilliant red shade color. And sticking with chlorine as the substitute, but moving that positioning to the R4 and R11 positioning. So bottom right, top left, we achieve the pigment red 209, which gives a little bit more of a dirtier red type of a color positioning and a weaker tint strength. So depending on what you're putting on and where you're putting it on will provide that the difference in color. But it also provides difference in properties as well. So this example shows us how that substitution and the type of substitution can impact the strength that it brings to your formulation. On the violet 19 side, where there are no substitutions, it's the polymorphism that impacts that strength of the particular pigment. The beta is going to be much stronger than the gamma. With the pigment red 122, where it's a methyl substitution on that R2 and R9. Again, bottom or top right, bottom left, we have a little bit of a difference in strength, staying with the same positioning, but swapping out the chlorine. Not a lot of decline in the strength, but if we stay with the chlorine and move over to the R4, R11, the bottom right, top left for the pigment red 209, we see a decrease in strength. So again, the choice and the type, the type and the positioning of that substitution will dictate the strength that you can achieve from those particular pigment products. Light fastness and weather fastness can also be impacted here. So same idea here. Only start to see this impact on the decline when we get to the red 120, red 202, excuse me, and the red 209, where both the choice of the substitute is chlorine, but it's the positioning that really impacts that light fastness and weather fastness. So if we go a little bit more into the detailed, so the unsubstituted version is, as I mentioned, the Violet 19. Two modifications, of course, it are the gamma, the red shade, and the beta is the more blue shade or violet shade in there. So both properties, because of the actual chemistry itself, is going to have very, very good properties, very good light fastness and weather fastness, excellent stability for heat, as well as no interactions with other pigments like TiO2 in the formulations. So on the gamma side, that polymorphism crystal looks like it's a matrix of 5 molecules with 4 molecules attached to a fifth one in the center. That's what creates the gamma crystal structure. This is created in the process by water drowning. As far as what this type of a pigment can do for you as a formulator, that high performance properties bring a lot to the party with respect to your formulation. It's very, very good for heat and weatherability, and not impacted with TiO2 from a photodegradation perspective. This is very important because there's in the red space, there's sometimes this issue for photodegradation impacts from TiO2. Transparent to opaque, depending on the product choice you make. It does provide some the FDA compliance for those formulations and applications that need it. From a crystal shape, this is a coatings developed type of a product. And so the crystal shape is kind of a thicker rod shaped area. Most of it is on the shorter end, so it looks like a sort of a barrel type of a shape. The other polymorphism crystal, of course, is the beta crystal. And this structure is a little bit more simple than the gamma, where it only has 2 molecules attached to a third one in the center. And this is created during the process by use of solvent drowning for this particular application area. And again, same like the gamma version, it provides those great high performance properties. As I mentioned earlier in an earlier slide, it's a very strong color, so it gives you even more high value in use area. So that nice violet color can go a long way for your formulation. It does offer some interesting formulation options to be able to reach some very nice color spaces. So combining with some inorganic pigments like CICPs, you can reach some very good color spaces that have exceptionally good hiding. And then the combination of the Violet 19 and the CICP offers very, very good weatherability perspective. And also this does bring with it the FDA. A lot of options here for these particular pigments. If we continue down in the substitution and start making our substitutions, the red 122, as I mentioned, is created by substituting on the R2 and R9 position, top right, bottom left, with methyl groups. Results in that magenta hue. From a overall chemistry perspective, Pigment Red 122 is sort of what I call a workhorse in all application areas. because it's used in inks and plastics and coatings. So there's just a lot of options to be able to use this chemistry to get that very, very blue shade magenta color into your formulation. Because it's a quinacridone, it does provide all those good high performance properties in here. And because I mentioned that it's a very good workhorse type of a color index, if you just look at the Sudarshan offerings, you see a lot of options in each of the application areas. So there's a lot of choices from an actual product perspective in this kind of chemistry. From a crystal shape, these are much more needle-like, so very thin and very long in nature. The TEMs that I have here are a coatings version on the left and a plastics version on the right. So they do have the same type of shape in there. The plastics version might be a little bit more thicker in the diameter than the coatings one, but they do have that long, narrow shape of a needle shape. Excuse me. So continuing down, so staying in that R2, R9 positioning, top right, bottom left, substituting now with chlorine gives us the Pigment Red 202, that very, very lovely red color. In this particular case, the gives us a more red shade than the one that came before us with the Pigment Red 122, which was a magenta. Again, it does bring those same high performance pigment properties along with it to get this particular color. And then finally, continuing with the chlorine substitution, but shifting positions to that R4, R11 position. So bottom right, top left, we now get to the Pigment Red 209, which is a more yellow shade red, a little bit more on the dirty side from a hue perspective than the Pigment Red 202. Not going to belabor the point here, except for the fact that Red 209 does have excellent transparency, so it's a very good choice for a formulation that might use effects in it, like aluminums and micas. So it allows that that full use of the shimmer and color that comes from effect pigments in these types of formulations. If we just take a little bit of a comparison look, I know I had it on some other slides here, but it's always interesting to say is from a formulation perspective, we see these are identical from a pure formulation perspective, but the positioning of that chlorine on that structure makes a big difference in terms of the end result color. So here's a comparison of the Red 202 and the Red 209. And again, it's just the positioning of those chlorine substitutions that makes all the difference in terms of how chromatic the red color is, as well as how strong the actual pigment is. Solid solutions. I mentioned earlier that quinacridones do play a big role in solid solutions, so they are good to know about. They're not as popular as the single quinacridones are. Two ways of creating them. The first one is more the more popular one, where it's a mix consisting of what is called a host compound, and then one or more guest compounds. If you look at the X-ray diffraction pattern of this one, it'll show like it looks like the host compound. The other area is just a mix of two or more related compounds. And what that looks like is in the X-ray diffraction pattern is that it actually does look like a new compound, a new structure, I should say. So some examples is Pigment Red 206. And this is a solid solution that consists of 2 parts quinacridone and 1 part QAQ, which is a quinacridone equinone, which is a very yellow compound. Unfortunately, this particular one by itself has very poor light fastness. So the solid solution in addition to with the quinacridone brings that light fastness back in line to look like the quinacridone light fastness, which is very, very good. This is results in a maroon in color. Very good properties. One thing to note that will, if you ever wonder whether the compound is a single pigment or a solid solution, you can always tell by the color index number. It's always going to identify both compounds within that particular solid solution, where the color index identification might be unique, like Pigment Red 206. The color index number does distinguish that there are 2 compounds within that particular chemistry. Another example is Pigment Orange 48. In this one, we're increasing the amount of the QAQ. So this one is a mixture of 1 part quinacridone, 2 parts of the QAQ. So we're pushing now the color to the more yellow side, so we get a nice gold or orange in color space. Again, you can identify it by those 2 color index numbers that it is a solid solution. Another example, and this goes to that second option from a solid solution perspective. Here we've created the Pigment Red 207, and this is a mixture of 2 parts quinacridone and 1 part Pigment Red 209, which is a single quinacridone that we discussed earlier in here. So this is that second mixture that we talked about. Again, you can also definitely identify it as with the color index number as 2 distinct compounds within that color index. So we've talked a lot about quinacridones and the chemistry that comes in there, and we've always had a discussion that the bulk of the properties, and we estimate that to be somewhere on the order of 75% of the physical properties of the pigment comes from that chemistry, and then the remaining comes from the choices from finishing. In this particular chemistry, there are 2 distinct and different processes to create quinacridone chemistry. They both are very, very different. They start with the same raw materials, but the route and the physical processing are different. The thermal or the solvent process, as the name implies, is done at a much higher temperature and does have a very high solvent demand. This was the process that was originally developed by DuPont back in 1958, 57, that time frame. The other process and is predominantly a little bit more widely utilized is the polyphosphoric acid process, or PPA. This is done at a lower temperature and is used to create those crystals by the drowning solvents. The drowning solvents are always going to be tied to a specific product. The examples that I used earlier with the violet 19, the gamma uses water, the beta uses as a solvent to be able to create those crystals. On the finishing side, that can be, there's a lot of choices to the pigment manufacturing R&D chemists when they're creating a product for the industry. They have a lot of choices that they can pull from to create the final product that they're looking for. And those choices come based on what kind of mechanical finishing they would like to use. as well as what kind of chemical finishing that they would like to incur to get the properties for the end application that they're designing for. So, and this is a very simplified dynamic of pigment manufacturing, but from a chemical perspective, choices are right after the crystal is created. The R&D chemists have a number of choices to use surface treatments or other additives after that crystal is formed to be able to get to that end application that they're designing for. The other area from a chemical perspective is at the very end of the process where the individual batches are blended into the final lot. There's always other options that are available to the chemist designing the product to add additional items to that particular product to be able to get their desired properties. Mechanically, in the choice of drying and the choice of milling. They are giving the R&D formulator options to develop how much hardness do they want in that particular pigment. What kind of a particle size and particle size distribution do they want for that particular pigment product? So all those choices, and there are many, are taken into consideration when the R&D pigment developer is creating the product that they've been charged to do. So they're using, just like you as a formulator, they're charged with the formulation of these pigments, and so they're going to also use their must-wants and nice-to-haves when choosing all the options that are available to them. So dispersion, so whether you're in plastics or coatings or inks, you all have to disperse the pigment in your formulation to get to your desired position for your end application. So you're going to take the pigment out of the bag that is in these clumps and loose agglomerates, and your goal is to get them to the finest position that you can, given your formulation and your process, and to have them stabilized at that point. It's going to go from several different processes within that full dispersion process to get there, but every application does the same, has the same need to get from that big agglomerate and lumps to that finest particle size. It all starts with the formulation, of course. I'm not telling you something that you don't already know. We try to help our customers in that formulation process to use a very simple formulation as a start. And this is especially good for those that are new to formulation. Is use the pigment surface area, divide that by 4, and that's a good starting place to determine how much dispersant that you might need for that particular formulation. So in this particular case, I have some violet 19s, both the gamma and the beta areas. I've listed what application they were originally designed for, the resulting surface area, and a starting point from a active dispersant perspective. So there's not a lot of difference between them. However, it's always good to know where to start. So in the following examples that I have, I'm going to walk you through what this might look like in terms of formulation in a number of different application areas. So the first example is in a solvent-based polyurethane. Both the gamma and the crystal are in this example. And in the target base that we use with that starting formulation is a dispersant level of about 17%. In this particular formulation, it calculates out to be just about a little less than 19% of dispersant. And you can see where the positioning of the color development is in these examples. For the gamma crystal, because it is that more red shade or yellow shade red, we want to establish the most red and the most yellow for this type of chemistry. On the beta side, we want to develop actually more blue in this particular case. So we can see where this formulation, this level of dispersion results in the color development. If we switch gears from a formulation perspective to a water-based decorative type of a formulation, um, again, the target dispersion amount was calculated to be 17%. This particular formulation is just shy of 8% in here. And if you remember the previous chart, the gammas ones are developing a little less of the red, a little less of the yellow, and the betas are not as blue in this particular case. So is this an optimized formulation? Probably not, because we probably think we can go more. So that's why when we give that formulation out, we always suggest to ladder both below that number and above that number when you're doing your initial screening, development screening. And lastly, in a water-based polyurethane, a very different formulation from the previous two. Here, the formulation that we use in this particular case is very high above the target area of 17 at just about 61% dispersion in here. Now, if I put all three of those on one screen to be able and put the scales at the same level, you can see how the color development in each of these uh, three formulations change with the amount of dispersant in that particular formulation. So these are the same ones that we looked at before, and the scales on this charts of the mass tone is the same. And if you just look down the charts and look at the amount of redness and yellowness developed for the gamma crystals, we see that it's more for that solvent-based polyurethane formulation. The other two are a little bit are pretty similar to each other, but less than the other. On the beta crystal side, the opposite is true. The water-based polyurethane develops the most blueness in this particular case. So it's always a good idea to do that laddering to make sure that you're hitting that that optimal positioning from a formulation perspective. If we shift gear to a powder coating formulation, again, we're looking at the gamma and the beta. So above the line are formulations that use the gamma, and below that line are the beta crystal formulations of the same type. So you can see where they lie in space. From a performance perspective, we saw earlier in some of the charts about the resulting positioning based off of the substitution, the location and the type. Here we're looking at the polymorphism and that impact. So this example is pellet flow for powder coating. And we see in both a 50-50 formulation with TiO2 and a mass tone formulation, the gamma does perform better with respect to pellet flow, so more flow out after the pellet flow or after the during the baking process, I should say. On the tint tone formulation, the 1090, there's just so much TiO2 there that it overwhelms the organic pigment, so you don't see that impact like you do in the others. The other performance area is in overbake stability. Same trend here, where the gamma does perform a little less than the beta in terms of the overbake stability. If we take a look at the color development in plastics, here we have several varieties of a gamma crystal pigment. And again, we mentioned earlier that for the gamma, we want to develop the most red and the most yellow in here. So we see how the finishing techniques impact that color development in this particular plastics formulation. From a performance perspective in plastics, there are going to be differences as well, and these are clearly directed at the choice of finishing. So we see that the filter pressure value, or it's a measure of the dispersibility in plastics, they are very different from one another. It is interesting to note that the ink product, which is actually an inkjet product, and a plastic product, do have very similar FPV values to each other. So you wouldn't initially think that when it comes to dispersibility and these application areas. Heat stability, primarily heat stability comes from the chemistry. However, it can be shifted some based on the choice of finishing. And this is an example of the choices for this coating product and the ink product I spoke of in the previous chart. Both of those choices do take away some of that heat stability. Still is very good and high, but it does diminish the heat stability a bit. And this all can be viewed with the TDS. However, it's you've always heard the terminology, always read the fine print. Here's one example of that, because if you look at these three products, that are ones developed for plastics, one TDS is for coatings, and the third one to the right is a ink TDS. They all have very, very different heat stability properties listed, primarily because the formulation that the heat stability test is done in is really the limiting factor for the heat stability, and not the pigment in here. So it's always good to read that fine print to make sure that you understand uh, correctly that it does have that high heat stability. However, in the coatings and the ink formulations, the formulation itself is the limiting factor with respect to heat stability. Shifting gears to Red 122, starting here with ink. We are looking at a nitrocellulose solvent-based ink formulation and a number of products within the Pigment Red 122 color index. Here we're looking at color development in the mastome area for all of these products. And for a Red 122, we want to develop, again, the most red, as well as the most blue, because it's a magenta color shade. We want to be able to get that blue shade. So you can see how the finishing choices in this Red 122 chemistry impact the amount of color development in this particular formulation. From a property perspective, we're looking here at gloss development and viscosity in the same formulation. So again, those choices that were selected for that particular product uh, do and can impact the physical properties of those particular products in here. So you have a choice of a lower viscosity, but then you might impact the gloss. Then the opposite is true as well. And typically, gloss development and viscosity are inverse to each other because usually that is related to particle size. Particle size usually tends to a decrease in particle size increases the viscosity, but also decreases or I should say, increases both the viscosity and the gloss. If you look at Red 122 in powder coating, Here we are taking a look at the color positioning of a variety of formulations the within this powder coating formulation, so you can see where your options are to use this. From a performance perspective, in unlike some of the things that we saw earlier with the violet 19s and the polymorphism effect, um, here we don't see impact with respect to the finishing choices used in this particular chemistry for the products. In overbake stability, we do start to see a difference in this carbon black formulation with this particular product. So the impact of the finishing choices does appear to have this impact on this particular property. One thing to note with Pigment Red 122, it is impacted by TiO2 from an exterior weathering application area. It is TiO2 negatively impacts the weathering in those very pastel tint tone type shades due to the photodegradation of the TiO2. And in the finishing choices do not impact that. In plastics area, this the same type of thing, filter pressure value or dispersibility, and the finishing choices that are made for this particular chemistry. We see a big difference between something that was developed specifically for plastics, very low filter pressure value, which is obviously a very good thing because there's such a short residence time with respect to dispersion in a plastics application. And then the coatings and the ink formulation, we see a very big difference between those filter pressure values, all through the choice of finishing. Heat stability, as I mentioned with the Violet 19, is generally directed by the chemistry. But in this particular case, there's more impact by the finishing choices, as you can see here with this data in here. So the choices of finishing do impact the resulting heat stability in a plastics formulation. So another thing to consider in weathering, a sub aspect of weathering is acid rain resistance. There are regions of the world where acid rain is much higher of a need to protect than other areas. So a fuming nitric acid test is used to simulate that pigment's response to acid rain resistance. In doing this test, we take a look at a 50-50 TiO2 ratio, and knowing that we've identified a number of color indexes that are very deficient with respect to this particular property. There are some that don't have this property, and there are some that I would say are probably on the bubble of this test. From a quinacridone perspective, both the Violet 19 and the Red 122 do show a deficiency with this particular test. To give you a visual, these are Pigment Blue 15-1s, and you can see the color difference in terms of the before and the after effect of the nitric acid in there. So it gives you a visual of the in the particular test. From a quinacridone perspective, again, that polymorphism difference that we saw earlier slide with respect to powder coating technical attributes, we also see it here with the Violet 19 gamma having more of an impact with respect to this particular test than the beta. The violet or the Pigment Red 122. Both have a significant deficiency with respect to this particular test. So we've always said this in all of our webinars that it's always going to be a balance to choose your particular pigment product. Like we do on the development side, we go through a list of must wants and nice to haves in our attribute list. You are going to go through your attribute list and assign those priorities as well. So you're going to balance the pigment chemistry and the finishing to get the performance out of that pigment that you are looking for. You're going to balance that with your application chemistry and process to make sure that you have that performance that you need for your end application area. So next month, we are going to further explore more polycyclic high performance pigments. That'll be held in April, last day of the month. And like always, you'll see that invitation come out about a week ahead of time. And then we'll continue the series in May, again, always the last Tuesday of the month, with another edition of the webinar series. So at this point, I'd like to open it up to any questions.